Hi and welcome back. We're going to look a little bit more at spectroscopy this time, and this time we're going to be looking at UV visible spectroscopy. So as you probably figure out from the name, this means that we'll be looking at transitions that cause light in the UV or visible spectrum. A little bit different to AAS, where we're looking at absorption spectroscopy with a hollow cathode ray of metals. This we're looking at samples that stay in solution rather than being atomized. So let's get going. So as with all forms of spectroscopy, we are looking at the way in which light from the electromagnetic spectrum or radiation from the electromagnetic spectrum interacts with molecules. In the case of UV and visible spectroscopy and colorimetry, which is a specific one based on, as you probably can figure it out, color, we will actually be looking at the visible spectrum again. So as with emission and absorption spectra, we are within the region of visible, but also with ultraviolet, we extend into this higher energy level of ultraviolet radiation as well. So this is the band of the electromagnetic spectrum of which we are operating within, which means we are looking at electron transitions, just as we were with AAS. So the basic features of a UV visible spectrophotometer, of which we have 3 at school, so hopefully when we get back on campus you'll be able to actually look at these and have a go at using one. We have a light source. Unlike the light source for AAS, which was a hollow cathode lamp made from the metal of which we wanted to investigate, this produces a white light that we can then tune to a specific wavelength using a monochromator. So this allows us to have a specific wavelength that we tune to be selected for the sample that we want to look at. This light pulse is then passed through our sample solution, which is contained with a cuvette. So we usually put a sample in here, depending on the size of the cuvette, between 1 to 3 milliliters. The light beam must pass through the glass or quartz of the cuvette through the solution, and then we measure with the detector how much of that light has been absorbed by the solution. Okay, so again, we are measuring absorbance within a particular wavelength of light, and this will allow us to work out how much absorbance of particular compounds is within our sample solution. So again, this time we're talking about in solution, so what we are analyzing for this must be soluble. Okay. They have detectors that are sensitive to both visible and ultraviolet regions of the electromagnetic spectrum, and the difference in light, again, is what we are recording. So the measurements that we take in this is due to the interaction of molecules or ions with visible and UV light. So this means that particular colors will be absorbed more, and you may remember back to your study of light in year 9, understanding that the color we see something to be is the color that it is reflecting back to us, and then minus all the colors that it absorbs. So that idea of light being absorbed and reflected is what this technique works on. As with AAS, the amount of light absorbed is proportional to the amount of substance present in the solution. Okay, so the more something is absorbed, the more substance is there to absorb it. And critically for this one, the color of a compound observed is the complement of the absorbed color. So let's look at that idea in a little more detail. As I mentioned before, when you studied light in year 9, you would have learnt that white light is made up of all the colors of the spectrum. So red, orange, yellow, green, blue, indigo, violet. This Roy Jabiv, okay, this being low energy for red and high energy for violet, comes from white light. White light is a combination of all of these. When something is green, all these other colors are being absorbed, and the green light is what is being reflected to our eye. We have a look here. If something appears green, then we know that all the violet is being absorbed. Okay, and this table, which comes from your textbook, textbook shows us the colors of visible light and their complementary colors. So if it is absorbing, if we have a 380 to 420 nanometer light, the light being absorbed is violet, and we will observe it as a green-yellow color. 420 to 440 nanometers, which is the wavelength of the light being absorbed, will be absorbing violet blue and will give a color of yellow. When we talk about purple light, it is given a wavelength of 680 to 780 nanometers. This color will be absorbing purple and will be seen as green. Okay, so you are given reference to this color wheel here that gives you an idea. So if we are seeing something as purple, okay, then if we're seeing something as purple, it will be absorbing light in the 500 to 580 nanometer wavelength here. So we see the opposite of what is being absorbed. So if we look at that for a spectrum, and this is a UV spectrum here, a UV Vis spectrum, we can see that compounds will absorb at different wavelengths. So don't necessarily only absorb at one, and this is actually the visible spectrum of chlorophyll, which is what makes plants green. And if you have a look here, it is absorbing strongly in the 400 to 450 wavelengths, and it is also absorbing strongly in the 650 nanometer wavelengths. But we see very little absorbance from 450 to 600. If we go back to our color theory, we can see that the 450 to 600 is our yellow-green spectrum, which we have little to no absorbance, but we saw a large absorbance in our purple and red spectrum. So if we overlay those colors onto this spectrum, we can see that all our purple and blue is being absorbed, okay, because it has a large absorption rating because the absorption is on the y-axis. Most of our red and some of our orange is being absorbed, but all the green and a lot of the yellow is being reflected. Okay, so these flat parts here are passing through. So this is not being absorbed. So this is what we are seeing as the color of the substance. Okay, so if I wanted to do an analysis in order to detect chlorophyll, I'm going to select a wavelength that would give me a high absorbance because that will make it more sensitive. Okay, so I could either go in the blue-purple range, or I could take a nice absorbance here in the around 660 nanometers, and then this will allow me to detect how much of that light is being absorbed, which would be proportional to the amount of substance that I have in my cuvette. When we do this, we can do this quantitatively, which means we can get a measurement for the concentration of the solution. When we use it in the visible region, we refer to it as colorimetry. And then, so the combination of this in a more sophisticated machine where we get to select the wavelength is known as UV Vis spectrophotometry. Okay, colorimetry, we tend to use red, green, or blue light. We don't necessarily use particular wavelengths. When we use particular wavelengths, we refer to it as UV Vis. So the depth of the color of a solution will increase dependent on the amount of light that's absorbed. Okay, so in this example here, where we have a dilute solution of permanganate, we can see more light would transfer through this than a more concentrated solution, which is almost opaque, of the dark permanganate ion. Okay, this is purple, which means that our yellow and greens are being absorbed, and we're going to be seeing our violets and reds being passed through the solution. So we will see the transmitted light, which would be violet. Okay, so the depth of color is related to the concentration. And as with AAS, we will create a calibration curve, which means we will do samples of known concentration, of increase in concentration, measure the absorbance for each of these, plot these on a linear graph, and then that will give us our calibration curve. When we do this, and we refer to this in AIS as well, we record a blank. So the blank is usually distilled water, but it's often everything in the solution except the thing that causes the color. We do this because these things can absorb some of the energy that we're interested in doing. So we do a blank, measure how much of the light is being absorbed by the solvent so that we can subtract that from the absorbance reading when we put the colored compound in so that we know what is the absorbance due purely to the compound. Okay, so the overall absorption is found by subtracting the blank from the sample to give us the portion of absorption that was due just to this, the compound itself. We use UV visible spectroscopy for measuring concentrations of substances, generally in things like body fluids such as urine and blood, hemoglobin, often of organic compounds, okay, so, and things that can be hard to atomize without destroying them. We can determine the amount of colored dyes in plastics. We can use it for detecting UV fluorescent compounds as well. We can use it for identifying the presence of metal ions, but AIS is far more sensitive and more accurate for this than what we would look at with UV vis. Usually for UV vis, if we want to determine the concentration of a metal ion, we'd need to make a colored complex with that metal ion so that we are able to see it, because not all of the solutions of metals are colored. Okay, you may remember that copper is one of the common ones, but not all of them form colored solutions. So the type of questions that we will see with this can ask us to give the color of a substance when we're provided with a spectrum. Okay, in this case, we're told it is a commercial dye and we are given the spectrum here. These large humps mean high absorption. So color in that region is all being absorbed. So if we have here, we see that we are absorbing in the yellow, green, yellow, red kind of wavelengths. Okay, which means the color that we observe will be the complement of that, what is being transmitted through the solution. So this flat region here is the color that would be observed, and we can see that this would be a blue-violet color that we would be observing this dye to be. The other type of question that we can see is in order to work out the concentration of something in a sample. And this will usually mean that we're given a table of results where we're given the absorbance, remembering that absorbance doesn't have any units, and the corresponding concentrations that went to form our calibration curve. Okay, so this is going to be our standard solutions that we use to form the calibration. These values here are what we plot to get our graph. So we plot these values here. And then we use the graph to interpolate what the concentration would be for our unknown sample. In this case, we're told that the concentration of iron in dam water is determined by colorimetry. The absorbance is a series of standard solutions, so this will be going from low to high concentrations of iron. Okay. And a sample of dam water is shown in the table below. So we need to determine the concentration. So the first things first, we need to plot our standard solutions on a graph of absorbance on the y-axis versus concentration on the x, because our absorbance would be our independent variable in this case. When we do that, we will generate this linear curve here. Remembering, don't force it through zero unless you're given a 0, 0 point in your data. Okay, so we're going to construct the calibration curve by plotting these points. Once we have constructed the calibration curve, we can then find the absorption of the dam water sample that we wanted to know the concentration. We're going to take that and interpolate down. This is where you need a good ruler and accurate graphing techniques to be able to tell us what the concentration is of the iron in that dam water sample. remembering it's going to be critical for you to check the units of concentration and that the units of concentration match your question. So you may have to do a conversion here, okay? So remember to look out for conversions. And remember, if you are unfamiliar with remembering how to do conversions, maybe look over that in preparation for this, because we do need to be able to convert from milligrams per milliliter to ppm and even molar concentrations. So make sure you are familiar with those conversions. Once we've done that, we can give our final answer. So the concentration of Fe2+ from this graph was found to be 9 milligrams per milliliter, making a note of our concentration. Okay, and that's all it really is. We're using the same techniques that we used with AAS in order to work out a concentration. Slightly different machine, looking at a different property, but same calibration curve technique. That means you're ready to have a go at these questions and the chapter review for chapter 18. And I'll see you in class.